Okay, can you hear me?
Yeah.
Okay, good. So I will present a bit the group of Madrid on effective field theory for collider physics. I will not be very deep in physics. I'm sorry for those who would have liked to be, but yeah, we are actually involved. Should I put the camera? Okay, wait a moment. Let's go to Zoom. Oh, wait, where I should I initiate? Why doesn't it work? Where should I go?
I mean, ¿estás compartiendo pantalla? Sorry, just we will fix the camera in a second. Let me.
Yeah. Oh, okay. Yes, right. Good.
Okay.
Then this. Okay, good. So you can see my face. Okay. So this is a bit, well, a list of people which are here in Madrid. Francesco is the head of this project, and then it's me.
In Madrid.
In Madrid. Yeah, Madrid. And then there is José Ramón Peláez and Jacobo Ruiz de Elvira, Alexei Vladimirov, and Pia Zorita. I put them in kind of different colors in the sense that we are doing things which are slightly different, but that are all involved in this project. Me, Alexei, and Pia are working more on hadron structure, pattern distributions, while José Ramón and Jacobo are doing more things in dispersion relation and meson and resonance physics. We have a bunch of PhD students. For students, for me, Alexei, and Pia, Patricia, Oscar, Sarah, Daniel, and Guillermo. Patricia and Oscar are the most senior, then Sarah, and then Daniel and Guillermo have just joined since September last year. While José Ramón and Jacobo have Pablo, Alba, and Alejandro. And some of them joined last year, some also Pablo is the most senior one. We have also one postdoc, which is Alejandro Briz Cuerpo, which arrived to us at the end of November of last year. As I said, there are many topics. I made a selection which is closer to my research line, and these are consisting of factorization, data analysis for TMD, and then all this study of properties of the distributions, like moments, resummation, jets, all things that we are doing now. I will not cover spectroscopy, dispersion relations, which are things which were closer to what HeI spoke about yesterday. So our general picture is the following. We have a physics of about 1 century ago, whose target was to understand the atom structure, so how electrons move around the nuclei. This kind of research led to quantum mechanics. And so it was extremely important for physics. Now we are left with we would like to understand the proton structure. And the interactions are electromagnetic, but quantum chromodynamics. The tools are completely different. And the way we are trying to do now is not to take a static proton, but an accelerated proton, and to study the distributions of quarks and gluons inside these protons, which take different names depending on the feature of the distribution. So we have a PDF, pattern distribution function, fragmentation function, transverse momentum-dependent pattern distribution function, and fragmentation function, GPDs, GTMDs. In general, all this set appears under the name of Wigner distributions. Current experiment cannot fix all of them, just a few of them. So we do what we can given our history. We start always with a definite process because we want to be pretty close to the experiment. So this is, for instance, the definition of the semi-inclusive deep inelastic scattering, where a lepton crashes against a hadron. The result is a lepton and a hadron and some rest. And there is a common structure in this experiment, also with the Drellian experiment. We have a lepton tensor and a hadronic tensor. Here they're indicated with the L mu nu and the W mu nu. The lepton tensor is trivial, is considered completely perturbatively, and while the hadronic tensor is actually the object of our study. Similar structure appeared also in the Drellian process, the one interesting for LHC. Also here we have leptonic tensor and the hadronic tensor, which result as a product of currents. So the product of currents from the point of view of operators are always the same. What change is the states. So the matrix element of these currents. Similar things can be done also for the plus and minus. In the top left, I have this hadronic tensor for the plus and minus in the case of a jet and anti-jet production. What happens to this cross-section? Well, we want to study them in the so-called factorization limit. So we are at an energy of the photon or the boson, which is exchanged, which is much bigger than the hadronization scale. And we want to look at intermediate scales like the transverse momentum of the photon or transverse momentum of leptons. So giving this order of scales, one can expand the hadronic tensor in a power expansion of Qt over Q. So we have a leading power, an next leading power, and a next to leading power. Up to now, say, up to 2-3 years ago, probably, most of the studies on this subject are concentrated on the leading power part of this cross-section. So it's the part which is definitely more developed than the other. And next leading power studies have just started, and next leading power studies, they are still, well, people are still thinking about them, just because of the difficulty of this stuff. So how do we manage to have an effective field theory? Historically, there have been several methods. One is soft collinear effective theory, which is strongly based on the method of regions for analyzing the processes and setting the modes of the expansion. Most recent one is the background field method, which is background field method is an old method, but has been resumed for this kind of studies very recently and appears to be very useful, especially for next higher power terms of this expansion. So let me resume a bit what we are doing. For instance, in background field method, we are supposing, I'm thinking here of a Drellian case where two protons crash to produce leptons. That so the hadrons are made just of what we call linear fields. They can be quark, anti-quark, or gluons. So each fermion or field has a causal and anti-causal component corresponding almost to negative and positive frequency field. So we can decompose the path integral basically in the hadronic tensor in this component. The action actually splits in a causal and anti-causal part. So we have an action which applies to initial particles and another one which applies to final particles. And once we have this scaling, which correspond to the fact that the momenta of these particles are ordered according to the powers of, say, transverse momentum over Q. Once we have the scaling, we observe that the fermionic field component have each one different scaling, but so these are the bosonic part. The fermionic part also can be split in two pieces, which have a different scaling, which here are denoted by Xi and eta. This division appears natural when we project the initial fermion with these n bar and slash projectors. These n are null 4-dimensional are such that n square is equal, or n bar square is equal to 0, and n bar is equal to 1. This is so they are light cone vectors. So if we decompose the fermions with these light convectors, we use equation of motion, and we see that actually two components are suppressed with respect to the other. And so we can perform our expansion. Then in background, we introduce what the background field and the dynamical field. We fix the background field gauge. These are things which we taken from literature. And we have something like this. So we have our current, which are in the first line. So our fermi are decomposing collinear, anticollinear, and the rest, basically. We expand in lambda, and so we have a first term, this is chi bar gamma mu chi, which includes, it's called chi instead of psi because it includes also Wilson lines. And then terms which appear in next leading power, like I have put here two terms, one which involves two fields and one which involves three fields. The one with two fields and derivative is called a kinetical correction. The other one is a higher twist correction. This is a three level. Then at a higher order, there are coefficients in front of these operators that should be calculated. Well, grouping things and going back to the hadronic tensor, we have actually the matrix element can be divided into a product of a matrix element, each one involving just one type of field, collinear or anticollinear field. And here I've given an example. There is some technical work to do, like field identities, Lorentz decomposition, and so on and so forth. But then we can separate the cross-section in parts which are purely collinear and purely anticollinear, and each one has its own properties under a renormalization group equation. This is an example, for instance. The first one is a leading twist operator, which correspond actually to a TMD. The one in the middle is a kinetic correction, and then we have a higher twist operators, for instance, which appears here. The notation, of course, the bigger the twist, the more complicated is the notation. So what do we do with this? There is a, what here before was J, now is F. We have these distributions that appears into the cross-section. We have a hard factor indicated with H in the cross-section, which is computed in perturbation theory. And we have evolution factor, which are here are grouped in these R. And with this, we go on data, basically, and try to extract these F functions, which are called TMD. When going on data, some caution should be taken in the sense that we have an approximation, so we cannot describe all the phase space, but just a region of the phase space where our factorization formula is valid. And nevertheless, for some of these distributions, which are the unpolarized case, a lot of calculation has been done perturbatively. For instance, the evolution kernel is known as 3 loops. And for these TMDs, we know its expansion in terms of standard PDF up to 3 loops. And there are also some non-perturbative correction on top of the PDF, which are not accounted for the PDF. The evolution, say, is very different for these multi-dimensional distributions. Say for the PDF, we have the standard digilap equations with the one normalization scale. With for the TMD, which depends on the Bjorken variable x, and this BT is the conjugate of the transverse momentum, so it's a dimension, space dimension parameter. We do not have one equation of motion. We have one evolution equation, but we have two corresponding to this rapid evolution. So it is more complicated, and we have the so-called Collins superkernel. This means that we should study how to fix the initial point of evolution with respect to the final point. We have studied this problem. We have come up with a prescription for choosing the initial state, and the prescription is such that we can choose the initial state such that all the anomalous dimensions are equal to 0. This is a perturbative definition, so we can use this kind of perturbative way, and a very stable, because if something does not evolve, does not change too much. So starting from this point, we have curves of null evolution, say where say the anomalous domain, the evolution factor is equal to 1, and from these curves on null evolution, one can go to a desired point, making so a smaller or a easier calculation. And this is how the evolution, our distribution appears. So we have this term in blue, which is the evolution factor, which is totally decoupled from this term in magenta, which is a completely non-perturbative function, which is completely scale independent, in the sense that it is calculated at this threshold point. Okay, doing this, taking all the possible perturbative calculations that have been done up to now. Last year, we produced a first result fitting the Drellian data. And the hard job here is to include all possible uncertainties, in particular PDF uncertainties. I don't want to be too long about this. We have a parameterization for a non-perturbative part, which at the moment is completely random, in the sense that we found this that works, but there is no particular reason for this to work. So there are some constraints on this, of course, but they're pretty loose. They're not so big. And this is the picture that we have. So for instance, imagine we have Atlas data. We have our description, which is correct in this red square. In the place that I say I call resum is a place where non-perturbative corrections, apart from the one of PDF, are pretty small. Then there is a region which is this marked by green square where perturbative calculations are valid, and the so-called matching region, which is usually it's better called an interpolation region. So people interpolate between the sum result and the perturbative result in some more or less consistent way. The cross-section that we have, once we factorize, is actually split in pieces which are non-perturbative. And for each of these pieces, we have to combine both perturbative and non-perturbative elements. Here it is how it happens for the Collins-Soper evolution kernel. So we have a part which is called a small b, which is perturbative, and then this DNP is a model that we have to put in order to have things converge. So this is the kind of result that we have for the cross-section. We see the progress improving the perturbative order in the reduction of the error. The main error here comes from PDF. Chi-square is a bit less than 1, so it's reasonable. And this is some of the results. Probably you have no time to go into each one, but you can see we have a LHC result in CMS, LHCb, Atlas. We have a RIC result in Phoenix and Star. We do not go just on the Z boson threshold, but we can go above and below the Z boson threshold. And so we have this CMS above the Z boson threshold. And we have also Tevatron results for similar processes. So we take all the results that have been measured in the world since accelerator exists, as far as we can. It is nice that we can compare some of our results extraction with the lattice. This is for the evolution kernel. And here we are the green one, a bit behind. Maybe. So there are several lattice people which try to fix this evolution kernel, at least in some region of this, in some interval of this B parameter. Okay, what are we doing in these days? We have redone a fit of cities, and this is data from Compass, and we see that we are very happy about this. So we hope to write a publication of this soon, say before Easter, and these are this. And we have our postdoc with Alejandro. We analyze the energy-energy correlators. So it appears that the cross-section for the plus minus with the energy-energy correlator is just a convolution of the cross-section for the plus minus into two hadrons. In particular, what enters there is this jet, which is a sum of hadrons and integral over Z of the fragmentation function. For this, we do not have a complete description of all the fragmentation functions. So we needed to introduce some non-perturbative part, which is not original in our fits. But once we do this, okay, we rewrite the cross-section. These are our preliminary results calculated by Alejandro. So we have result for Opal, say the old E plus E minus experiments. And this will be interesting also if one wants to study this stuff for the future circular collider, E plus E minus. So making prediction for that is something that we can do. On JET, we have a program of JET in collaboration often in collaboration with NICEF, with Voter. Why JETs? JETs because They are a more symmetric object with respect to hadrons, a more stable object. Of course, there is a problem of jet algorithm, jet axis, jet radius, so that have to be taken into account when we have to this factorization. And this is, we have done it with water in a series of studies, and there are some other groups that are doing. This is one of our latest results. We're trying to get cross-section at net splitting power using jets. Okay, and this is the picture that we have. Say, if you see the green lines in the left plots, we have a jet which is not created by quark, but by quark and the gluon. And this is a typical effect of a higher twist. Okay, then this object emerges into one, and this creates actually the jet. So in that paper, we said the case of the plus and minus, and now we are going to do for series. But okay, one can do more. The other things that we're doing is moments. Basically, we can integrate our distribution in transverse momentum, taking various powers of transverse momentum. And the key question here is this, actually. If you have a transverse momentum dependent part of distribution function integrated over transverse momentum, you expect to get something similar to PDF. The point is that this integration is divergent, so you cannot go straight, at least in theory, to do that. So what is the way out? The way out is to set the top of the integration as an upper cutoff, and setting this as the scale of the collinear distribution that you have after integration. If you do this, you discover that your integrated distribution is not the standard integrated distribution. We call it integrated distribution in a TMD scheme. But it has a normalization group equation which is very similar to DGLAB, but it's not DGLAB. So in order to pass from this integrated distribution to the standard one, we have to calculate a factor, a multiplication factor perturbatively. And nicely, we discovered that this correction appears to order alpha square. So it's a small correction. It's not a big one. For some of them, we have up to ordinal alpha s to the cube already from using present calculations. And so this is the final formula that we have. For instance, we want a PDF in terms of the integrated TMD. We have to make this integration and then renormalize with this perturbative factor. This is a plot of the graphs that we have. And what we discover is that we have an agreement up to less than 1%, basically, when we go into a low. And our integration scale is bigger than 5 GeV. So below 5 GeV, things do not converge too much, but above 5 GeV, things are very precise. So I hope to have given you some overview of things we are doing here. But in general, we are open also to new things or things which are related to ours, but from a different perspective, like operator resummations, which I've been hearing yesterday. And this can help our job or provide new insights on what we are doing. All this stuff are neural network methods, and for the moment, I've seen them just in collinear physics, but not in these multidimensional distributions. So it's nice to study this. I've heard about energy correlators in some framework. I don't know how this can be related to what I have shown here, but certainly something which we can talk about. Jets is a huge field, and there are also in this case things which can be connections. One of the motivations for this, we have a several connection with the NICEF and Torino group, especially for this part of distributions. The people who are doing the special relation in meson physics and bootstrap methods have also connection with the part of José Ramón Peláez and so on in Paris. And there are new things that we would like, we are eager to explore, like bootstrap methods, conformal symmetry for partial distribution studies, for with the soft collinear effective theory, arriving to Reggio theory, and so on. All these things which we can discuss about this. I think it's all for me.
Thanks, Ignazio. So do we have questions for Ignazio? We can have them now or after vote in the discussion.
Can I ask
I
one?
have okay.
I was curious about your compass results that you were showing at the R25.
Mm-hmm.
Because on the left-hand side, there's some things that are not, don't look like they're working very well. Yeah. Down in this area. What's going on there?
Okay, now consider that Q square is extremely low, from 1 to 1.7. So
Oh, yeah, I couldn't quite read that, so thanks. Yeah.
okay, so the factorization breaking terms are pretty big. And so, in fact, we do not include this stuff in the fit. If you see the dots which are filled are included in the fits. The dots which are empty are not included. And here, because of this scale, they are so small, and we see that it's pointless to include this stuff in the in our fits. This is yeah, it's always the case that the CDS data are always at the energies much below the Drellian data or the plus and minus data. So, and this is nice and bad. Nice because we explore different regions of the first space. Bad because there can be corrections in the CDS case which are not present in the Drellian case. I'm referring to power corrections, which we take into account only partially. So we have non-perturbative elements that we fit, but we do not have yet a study of all possible power correction which can enter here and things like that. So we see they're reasonable. Our results are reasonable, and yeah, but things can be improved.
Okay, thanks.
Hi, Ignazio. I wanted to ask a question about this expansion by regions. Can you comment more about that?
Yeah, there are. It's not a thing which I'm really working on this, but there are people in the SCAT community, in Stuart and so on, that try to arrive to Regge equations from the point of view of collinear effective theory. I never entered this kind of game, but it's not a game which is far from what we are doing now. So if someone is interested and want to start studying this with a point of view of collinear, we can start to discuss. This is the thing.
Okay, thanks.
So I also have a question, and you showed some comparison with lattice results.
Yeah.
That was about which quantity was compared? Can you remind?
It's the Collins super evolution kernel. So we have an evolution kernel, and what we have done is to separate the evolution kernel from the distributions. And this could be done because of this zeta prescription that we did, actually. Otherwise, this separation is not so clear. I cannot go up and down.
It's not.
It's stuck. Okay. Let's see. Anyway, and on the other side, lattice cannot calculate everything because so this is one of the things that they can calculate and for which we can have a comparison.
I mean, my question is motivated by the fact that if there is a comparison with lattice, then somehow in the what they've done in practice is to solve some big Hamiltonian. So maybe there's a connection with machine learning methods, and
I must study that.
could be.
May I comment here that in this case it is not possible because no direct measurement. We do not really measure this Collins superkernel. We measure something different, and then we more or less extract from this measurement Collins superkernel.
Ah, I see.
They do Lamet, basically.
No, it's not Lamet, but okay, it's long story, but it's not direct measure. It's not like mass operator or something like this. It's something else.
So you also showed some. Why can't you go back?
Because I cannot go back. I'm stuck. Where can I go?
I think Boder did something highlighting your screen. Maybe
What is your fault?
Can you do?
Yeah, I can't do anything. Ah, okay. So calling superkernel. Yeah.
No, I mean here. This parameterization for NP looks like a simple function. Is there an equation for it?
No.
Is there a first principle equation for it?
So the constraint that we have is this stuff should go to 1 when this b parameter goes to 0. So any function can work. I expect that when b goes to infinity, this goes like an exponential e to minus b or to a constant, or to something around. Here we force this to be exponential. So exponential is motivated by, say, meson scattering. Usually they have this exponential form. A constant is people doing small x would like to have this to be a constant when in their limit. We prefer this exponential decay, but well,
I mean, what I'm saying is not an observable. That's why you don't have an equation.
it's not well. What is observable is the total TMDs. Okay, this is observable. So we have, if you like, this is the question at the bottom. This is what we observe. This is what we can plot. I don't know if I have a plot in my back slides, but this we can plot. This is something like a PDF we can plot, or we can use physical, almost physical.
I see.
Yes, but each single part is
I see.
more like this. So this is the object which appears in the factorization theorem. So.
But what is good that for this object, we have operator definition. So if you have any ideas how we can build some operative model to describe this operator definition, that would be nice.
Yeah, operator definition are like the first line is usually the operator definition of a TMD, basically.
I see.
And this is what is the JY1 is the F which is written below, and this depends on the flavor. It's not written here, but yeah.
I see.
So the good thing is that all non-perturbative quantities that we have a corresponding operator definition. And for all of them, we know the evolution with scales. So we can say, okay, this is completely non-perturbative at some scales, then I make the evolution, but say you have
I see.
a consistency in the non-perturbative parts are not introduced by chance. They are consistent with all this factorization.
I see. So, but the equations are not linear, right? In the
evolution equation.
The evolution equations.
No, they're linear. They're linear.
They're linear. I see.
Yes. This here on the right column.
Okay. Thanks.
Yeah. Now, this equation has been in the market since 40 years. It's not really.
Yeah, I think people in work package 1 are not fully familiar with the factorization theorems, and now they are and the way they interplay in this kind of computation. So I think that's mostly the
what we are trying to do if I understood, is try to resum a class of operators to all orders in some sense. Now, the origin of operators, I don't know if this comes from a factorization theory or is just from a model or a general theory that you have. Sorry, but what we have here, for instance, is what Alexei, for instance, has done in some. Let me go here. For instance, if you look at this intermediate, what we have here, we have these operators in the last line, which has just two fields, but just things which depends on derivative. So this kinetic term, Alexei has tried to resum them at all powers.
Yeah, I remember. Yes.
So we have, say, during this expansion, we have some some things, and we can think to make some partial transformation of all this stuff. Sometimes it works, sometimes it doesn't work.
I see.
And this is
I mean, maybe in the discussion we can ask also Volodia if he has some other. I don't think this kind of game was played for N equal 4, or, for example. I don't.
for n equal 4.
Or at least I don't
no.
know. Maybe some people know.
No, I don't think so. We just concentrate on phenomenology and we didn't. But for n equal 4, and this stuff of energy
I mean,
correlator is for n equal 4, yes.
Yeah.
There are
That
stuff.
yes.
Probably that can be the starting point for the discussion.
I
Something
see.
which is common here and there, and then see what happens.
We also have seen some studies in n equal to 4 about Colin superkernel.
Yeah. Oh, you know what?
Yeah, they relate to this correspondence between jets and Colin superkernel and higher order computation in n equal to 4. I don't know how helpful it is here, but
I see. I mean, what I'm trying to say is that these as operators, they look complicated, but then you want to integrate them. So they're going to give you some functions that maybe at the level of the function that they give you, you can have a better classification, like rather than following from the microscopic definition to the function you want to study. It's a long way because you need to pass through the operator, do the actual integration with fields. But maybe at the level of function, then it's kind of so let's say each time you add an extra order in perturbation theory, do you expect to get some do you expect to increase at the level of the fit? Do you expect to increase how much? Like do you expect to have a new function that fits better, or is the same kind of stuff that more or less gets addressed by, I don't know, more power of more polynomials of S, something like that?
No, we have that. So we have a power expansion, which is this one, and a perturbative expansion. Now, usually the perturbative expansion does not break the power expansion. So first we do the power expansion, then at each power we calculate all the orders of alpha S that we can.
I see.
Okay, now there are some cases where this is not strictly true when you go to heavy quark cases and things like this. Then each gluon you add, you also generate new operators. And so what?
I see.
This is not the usual thing. The most, I mean, the best thing is when you calculate alpha, you don't change your basis of operators. This is
I see.
we have cases like this. So.
Thanks.
Welcome.
So if there are no more questions, I don't see questions. So maybe Voter, you can take the word.